So can everybody hear me? Okay, good. Thank you. So as usual, I'm gonna wait for about 1 minute. 그 참여하는 분들 다 잘 들리나요? 그 안승민 씨나 뭐 이동민 씨, 장충수 씨 잘 들리나요? 예. Okay, so let's start today. Okay. So, okay, the main topic that we're gonna cover today is continuation. This is an overview. So the topic that we're gonna cover today is something called continuation. And maybe some of you already encountered this idea of continuation in your programming language course. So in fact, the idea of continuation appears in many places, not just in computer science, but also in mathematics, also inside the computer science. It appears in logic, in semantics, and as a construct in programming languages. So I'm sure that most of you are familiar with something called goto. Although you're not going to use it very often in maybe the Java-like languages or C-like languages, there's a programming construct called goto. And then sometimes some other things that also appears in programming languages, exception. Perhaps if you take a programming language course, you might heard about something like a core CC or continuation passing operator, or sometimes called control operators. And I think the modern programming languages sometimes provide something called coroutine. And they are used for implementing something very crazy in those programming languages. So these are some programming language construct that appears in, that's there to support the change of control. But the underlying principle behind all of these is continuation. So this is continuation that appears in PL, but also in semantics. There's an idea of continuation. That's what we're gonna cover today. And then although we are not going to cover it, there are something called weakest precondition that appears in automated verifications and also in some semantic study of programming languages, especially that's the one that used quite a lot by Dijkstra. And that is also can be understood as a continuation. In logic, this continuation is closely related to classical logic, where we have double negation. So in classical logic, you have some implication, which is not P implies P. I mean, this is true in classical logic. But so in Korean, it's called 대중률. But in this is true in classical logic, but not true, and not necessarily true in intuitionistic logic. And then it turns out, and then this is very closely related to continuation. Okay. And then also in mathematics, there are many concepts called the dual space. So what that means is if you have some space L, I found this. So if you have some space L, then often you are thinking about mapping that takes element in the space and returns some element R. So there can be a vector space, and you think about something like this. And some special property like linearity and so on, that's often called like L star. And this is used quite a lot to carry out various studies, and then especially in functional analysis, that also is very relevant to machine learning. And these are the kind of things that are all closely related. So what's going to do today is I'm gonna introduce this continuation from the semantics perspective. And especially we're gonna study continuation as a mathematical tool to define the denotation of semantics. And I'm gonna tell you why we want to do this. And we will use, so our plan is to study continuation in semantics, or you can say continuation semantics, which means that semantics that uses continuation. And then we were gonna use a programming language that we studied so far. The imperative programming language with failure and input-output. Yeah, failure and input-output. Okay. And I mean, this actually is, especially working on the denotation of semantics it's guided by two major criteria. One is more like a beauty. So somebody who work on denotation of semantics of complicated programming language, they want to come up with a simple mathematical setup that explains what's going on in the programming language as a whole. So once somebody understands a little bit about the semantics, then they can talk about what are the inherent principles or inherent properties of the programming language, not the programs in that language, but entire programming language itself. So make the key properties of a programming language very clear, and make it into a part of nice math. That's one objective of denotation of semantics. And another objective is more like an application. Somebody who work on denotation of semantics, they want to use it to justify, some program analysis tools and also program logic And also they want to use denotational semantics to justify compiler optimization and so on. But one thing that I'm gonna emphasize quite a bit is that actually using this continuation semantics is in the programming in denotational semantics has some nice aspects, which is it make it clear that each program construct does the two things. Each operation in our language does essentially two things. Okay. This is input. Two things. The first is what are these two things? The first is a state transformation. So it produces the output state. And the second thing is that it change control. So if you think about computer program, what it does is that it keep updating the state of a machine. But at the same time, it changes each instruction in your programming language. Also decide which instruction to be computed next. Okay, maybe your instructions say computation should stop now and then just return the result to the user. Or it may pick another instruction that needs to be executed next. So each instruction in a programming language, in this type of imperative programming language, does state updates. I mean, potentially does state update, and also it decides which instruction to be run next. So if you took a course on some very low-level stuff in computer science, then especially like assembly language and so on, then you learn about there are some register called program counter that decide which instruction to be run next. And that is very inherent property of each instruction in programming languages. And continuation make this aspect very, very clear. Okay. I mean, maybe when you hear about this semantics first, it's not entirely clear to you that, I mean, this changing control aspect becomes explicit in this continuation semantics and is a bit implicit in the semantics that we discussed so far. But once you study about this a bit more, then you can understand that this is what's really going on. And okay, and then other things that we are not going to talk about it here, but we will discuss it later when we study the functional language, is that the continuation semantics is more general. So it let us explain a programming language which have some construct that I wrote over there. That's called in courses C, exception, goto, and so on. So more complicated language can be explained in this continuation semantics style. So then the question becomes, what is continuation semantics? And then also the question is, we said we're going to use it, how to use it in semantics. So the continuation is nothing but intuitively let's start with the mathematical. Continuation is an element. So I'm going to usually write it as a kappa, which means, that has a similar sound as a C. So and then this is an element kappa that map from take a state and return omega. So it has the same form as a semantic command that we used before, but intuition is very, very different. Okay, what it represents is that it represents the rests of the computation. And we happen to, it happens that we are using omega, but this is, some people just use it, some set called answer, because what this kappa does is that if we are given a command, often, we're given a continuation kappa implicitly. And what this kappa represents is what should be done after this command C is finished, okay? And then so K represents the rest of the computation that should be run after the command C. And maybe the command C, if it decides to complete or finish, then what's gonna do is that it will skip this continuation kappa, and then it will just return the answer directly. So that's one thing that command C can do. Or this command C will say, okay, I'm not going to disrupt expected flow of computation. So it will finish the computation and just invoke kappa. So here's a typical scenario. I mean, this is all informal discussions. Typical scenario. So if I have a command like assignment, and then if this command is given in semantics, continuation kappa, and initial state sigma, what it's going to do is that it will update state sigma so that the states, the variable x will have a new value according to the assignment. But then afterwards, it will call continuation kappa, because kappa represents the rest of the computation, which should be run after this assignment C, this assignment. So what in the semantics has to do is that it's gonna provide this final state to the continuation. In other words, assignment doesn't do anything special for change for the control. On the other hand, this is not a correct definition. That what I'm gonna tell you is not 100% correct, but it roughly gives you some idea about what kind of things we can do with continuation. So suppose we have a fail. Okay. Then we are also given continuation kappa and initial state sigma. And what fail is supposed to do? What fail is supposed to do is stop computation completely at this point. Okay. So it will, instead of calling continuation kappa with the current state sigma, it's just gonna return sigma. Okay. I mean, this, as I said, this is not 100% correct, but it's gives us some idea about what's happening. So for assignment case, we call continuation kappa because assignment doesn't intend to stop the computation, but for the failure, its purpose is to stop the computation at this point. So it will not call kappa, and it will just stop it, and then it will return the current state sigma as the final outcome. So having kappa allows us to express this intended behavior of, this second aspect of the instruction, which is how they are going to change the control of the execution much more explicitly. And if you compare this with what we did before in denotational semantics, in the denotational semantics, when we use, fail, if we give a sigma, we said, oh, we're gonna record it, this is an abort state. And then if we have an assignment, we said, oh, this is just normally terminating state. So we marked, in a sense, state with a tag, which say whether it's an aborting and termination. And then we require the rest of the semantics to respect this mark. So if you have this appeared in the sequential composition. So if you do the sequential composition, we said we run C1 first, and then C2, but we run it on the lifted mode with the star. But what this star does is that if it encounters the normal termination, it just runs C2, just like we are calling continuation after the assignment. But if it encounters abort, and it doesn't run C2 at all, it just returns abort sigma as a result, just like what's really happening here. So the point I want to emphasize here is that in the continuation semantics that I'm going to tell you, this management of how the control should change in the program execution is done when you interpret assignment and fail. Okay, at the point where the control change actually happens. In the case of direct semantics, I mean, this is called direct semantics. That's the one that we studied before. This change of the control is done indirectly. The guy who changed the control do some marking by putting abort and termination, and all the rest should respect this marking. Okay. So the one above is more explicit, the one below is less explicit. So let's do it a bit more formally. So as I said, the continuation is nothing but mathematically a mapping from states to omega. But this omega should be understood as a final answer. So as I said, sometimes instead of in some setup in the continuation semantics, they are using some different space answer instead of omega. But in our case, it happens to be omega. This is a final answer, and we represent the rest of the computation. And now for the continuation semantics, uses continuation to interpret program. And this semantics has the following form. So as I said, the most important part of the semantics is interpretation, the shape or type of the interpretation function. I'm going to write it as like this, continuation. For expression and Boolean expression, the semantics has exactly the same. Semantics is exactly the same as before. It's only changed for the interpretation of a command. For command, we have a map. But this map the beforehand, the semantics was it take the current state and return omega. So that is what we wrote there. And we can put C because sigma is a discretely ordered continuous function and all the functions are exactly the same. But in the continuation semantics, we take one more. So we can just put C here to make it clear. We are really working on the continuous functions. It takes something extra, like this. So this part is for continuation. And this sigma is an input state. And this omega is a final answer. Let's say ultimate final answer. And this omega here is also represent the ultimate final answer. So in the continuation semantics, we have instruction like this, C quant. Now the first parameter kappa is coming from this continuation. Then it also takes a second parameter sigma that's input state. And then it returns something in omega. Okay. Now the question becomes, how should we interpret this? And if my vague explanation somehow make you understand basic idea of a continuation, then you will be able to fill out the rest of what's really going on. But if that's not the case, then here's a more formal way of capturing what I told you before. Okay. So how should we complete this? And then some guidance coming from correspondence between this continuation semantics and the semantics that we covered before. The semantics that we covered before, which I just write it like this, it takes a command and return map from state to omega. Okay? And then we may ask, okay, how, the intuitions about continuation that I told you actually describe some formal relationship between these two semantics. They say that more specifically, it tells us if we have any command C, if we interpret in the continuation semantics on the kappa and give a initial state sigma, then what should happen is that we should run intuitively command C under sigma. And if C gets a final result, we have to run kappa. Okay? And if we express this directly using the direct semantics, the previous semantics that we covered, that corresponds to this. We run command C under sigma. And then we're going to run this kappa lifted, okay, with the star. So this is the relationship. And then from this relationship, we can derive, in a sense, the semantics, continuation semantics, which is defined in a compositional way. Okay. How you do it. So I will give you a few cases and ask you to fill in the detail. And at this point, I'm not going to consider fail, although fail is a really important part because fail raises another questions that we have to think about a bit more. Okay, so how we do it? I mean, so we do that because it's defined compositionally. We do case analysis. Well, you can say it's a syntax-directed definition. We do case analysis, and there are a few cases like we have a skip, continuation semantics. Then we have assignment. And then we have sequential composition. Also, we have if then else. And we have while. And we have input. And we also have an output. Okay. So in each case, we plug in kappa sigma as an argument. Kappa sigma. Then we have to provide a definition on the right-hand side. So I will fill in the few definitions and I'll ask you to complete the rest. And so for the second case is the one that we covered. We said, and to be more precise, what we have to do is that we run continuation on the state which is properly updated by the assignment. So the kappa represent the rest of the computation, and so we change state according to the assignments. Assignment doesn't change the flow of control, so we just provide this updated state into the continuation kappa. And then for if then else, I mean, maybe what I do is a sequential composition. Yeah, so for sequential composition, what we have to do, we run the first command C1 under continuation semantics on the state sigma, but we will change continuation. Okay, what the continuation means? Continuation means the rest of the computation. So when you run C1, now we know that we have to run after C1, we have to run C2 and then kappa. Okay, So the continuation here now changed. So this is a notation that represents the functions. This continuation take a sigma prime, and then it will have to run C2 and the rest of the computation. So that's why we are using something of this kind, continuation kappa sigma prime. So if you want to be more abstract, I mean, this having the lambda and then just having this with the lambda sigma prime and applying it directly, that's the same as just writing like this, partially apply the function C2 kappa. So more abstractly, or more succinctly, it can be written like this: C1 continuation, C2 continuation kappa, and sigma. Okay, so then for the inputs, okay, we have to run continuation kappa after the taking the input. Okay, so we use this construct. I mean, so if you recall, we run about this I term, I abort, then I in, I out, I bottom. They are the 5, in a sense, constructors of elements in omega. And then I said we can define any functions from omega by doing case analysis on these. And so in this case, we said we're going to use this constructor for elements in omega, and which take a function. So that function takes input value from the user. And then based on that input value, we update the state, sigma, so that variable x store this input value. And then for this updated state is going to be provided the continuation. Okay. So you see that this is now super simple than as before, but it simplifies many of, in a sense, type changing operations that we used before. So now here's my question, fill in the rest. Okay, what's going to be in this case? Maybe. Yeah, to fill in the rest, that's the exercise. I'll give you 5 minutes to do so. The case for loop is not very easy, but I want you to think about this. So what's going to be this, this. So that's an exercise. Okay. And also, if you solve this exercise quickly, then I also want to encourage you to think about how to prove. This statement. So that's a second exercise I want you to think about. I'll give you 5 minutes to solve both of them. I mean, focus on one. If you can do it one, you can move on to number 2. Okay, so let me tell you how to solve them. So the first, so here is, this one is also very simple. I mean, if intuitively skip doesn't do anything on the input state, also doesn't do anything for the control. So what does that mean? That means just apply current state sigma to kappa. Okay, it doesn't change what should be the rest of the program. Okay, so, and then for the if then else, what it does is that it first check Boolean condition is true. If the Boolean condition is true, so then we run C1 with its own way of handling the rest of the control. Otherwise, we run C2 with its own way of handling what the rest of the computation should be. Okay. And now let's think about this, I mean, the output case first. We do the outputs, but then the value which is output is an expression E. And then the rest of the computation should be the one with, with this kappa. Okay, so we just run the rest of the computation and then update the state. State is not updated, so we just return the sigma here. Now for while it's a bit more challenging because we have to use a fixed point. So we use fixed point. But some interesting part is that we compute the fixed point on the continuation space. Okay, so this is continuation space. And then we define operator called F. With fixed point, we're going to compute, and then we run the sigma. Now, what this operator F does, it takes, you can think of operator F a continuation transformer. It takes a continuation, and it returns continuation. And it's defined like this. It takes continuation kappa prime and current state sigma. And if the current, let's call it sigma prime, if the Boolean conditions of sigma prime is true, so then it runs the body of the command. But when you run the body under the continuation semantics, we provide this kappa prime, the input kappa prime, as an argument. So kappa prime represents the continuations from the after one iteration of the loop until all the way until the end of the computation. So we provide the kappa prime, which captures all the rest of the computation plus the remaining loop iterations. And then we run sigma prime there. Otherwise, so this is the important part, beforehand, if the meaning of the while loop, we just return the current state sigma prime. Now, instead of just returning sigma prime, we have to provide, we run continuation, which is the input continuation here. So we run input continuation kappa and sigma here. So if the sigma prime. So if you unpack this fixed point computation by really unpacking this, the YF, which is computing Fn bottom n is equal to 0 to infinity, and it provides a sigma. If you compute this, the Fn bottom, and then you will see that it really build up continuation initially from kappa, and then we add C to the before. What I mean, it prefixes the computation of C before kappa in F1, and prefix come to it iterations of the loop before kappa in F2 and so on. Okay, so you keep adding something extra computation before this given input this input continuation kappa. If my explanation is confusing, very likely, so then you can just look at this definition and then take it as a semantics. So that's the semantics, the solution for this exercise. The second exercise is actually requires some more work. So because if we don't have a loop, this second exercise is not super difficult, but with a loop, it requires some more work. So what I will do is that I will explain to you about how to prove this second exercise in the absence of loop. And then in the presence of a loop, I will give you a hint. I'll go cover all the materials of today. And if I have time, I will come back here and then tell you how can we deal with this loop case. Okay, so how to prove this? So for the seconds, let's assume that our language doesn't contain loop. Why? This is wrong. Our language does contain loop, but let's say this is not the case. And for this small, the restricted version of our language, we can prove this correspondence. Okay. So and then the proof is, we prove this by structural induction, which means that we do prove this by case analysis. How to do this? So we consider the simple case. So the first case to consider is a skip. In the skip case, the continuation semantics of skip kappa and sigma, that was kappa sigma, okay? Kappa applied to sigma. And then now if you compare this with, so we have to show this guy is the same as lifted kappa applied to the normal semantics of skip of sigma. Is it going to be the same? So that's what we have to check. But if you compute this this kappa star on the outcome of a skip sigma, skip doesn't do anything, but it put a tag which says terminating state. And then the definition of this star lifting, say if the input is the normally terminating state, we just apply kappa. So we just show that these two things are equal. So this is okay. And then the other case for assignment case is essentially the same. So we're going to cover sequential composition case, which is more involved. So it says sequential composition, continuation. Then we have to use induction hypothesis here. So this one is saying C1, continuation semantics with the new state sigma prime, C2, continuation semantics, kappa, sigma prime, and sigma. So that's the definition of the semantics. And then we have to show this guy is equal to kappa star, C1 direct semantics applied to sigma. Okay. So for this case, we unpack the definition here. What was the semantics here? It was kappa star applied to C2 star and C1 sigma. And then although I'm not going to show this to you, if you take something and then apply the lifted version, lifted things, and then apply another lifted thing. That's the same as in this guy. C2, and then lifting outside. Okay. So if you take these two things, one after the other, and then doing this in one go, they are producing the same result. That's related to the associativity of sequential compositions in programming languages. C1 sigma. Now, at this point, what we do know is that, by using induction hypothesis, this one is the same as C1 continuation semantics. Kappa star, C2, and initial state sigma. But if I look at this kappa star and sigma and this C2, and now if this is by induction hypothesis, and if you use induction hypothesis on C2, then we do know that kappa star and C2 sigma is same as C2 continuation semantics kappa sigma. But the left-hand side is really kappa star C2 applied to sigma. So for both sides, really say induction hypothesis tells me kappa star C2 that is the same as C2 continuation kappa. So what this tells us? This tells us we can replace this part by C2 continuation kappa. So this is some side calculation. So what we have here is that's the same as C1 continuation C2 continuation kappa sigma. That is exactly the same as what I wrote over there. So these two things are the same. Okay, so this is how you can handle the sequential composition. And then other cases, except loop, other cases are not not very difficult either. You can prove this without problem. So let's handle one more case and move on to the next topic. The one more case is input. So we said input case, continuation semantics of the input, kappa sigma is iota in with input n, and we run continuation kappa where current state is updated with this input. So that was the continuation semantics. And then if you compute the direct semantics of x sigma, and then direct semantics say something like this, that we take input, and then after taking the inputs, we update state sigma with this value of the input. And then that's going to be the normally terminating states with state sigma where x gets updated with the input value n. Now, if you remember the definition of this lifting, say that if we have an input, we just apply this operator to the outcome of the input and after what's going to happen in the input. So the same as from the n kappa star to the output term, the same thing. But then because it's a terminating state, if you apply the kappa star, that's just the same as applying kappa directly. So that's the same as the n kappa applied to sigma xn. And then we can see that this one is same as the one above. They are the same. Okay, so that's how you can prove this. And so if you haven't done it, I encourage you to prove the output case and then if then else case. And both of them will have a very similar pattern. Okay, so that's the basics of continuation semantics. So we haven't dealt with one more clause. So one extra clause here, which I forgot to include, is a new variable declaration. New var. You can see. So in continuation semantics, it takes continuation and then current states. And then it does something a bit interesting because what does it do? It updates state sigma with this variable x so that the variable x has this initialized value. And then you run the command C. But after the command is finished, we have to restore the value of so we have to restore the value of the global variable x. So that's going to be done by this continuation. So our continuation will be changed. We take sigma prime. Then instead of applying sigma prime to kappa directly, we change sigma prime. So that this variable x now have a original value under sigma. So, in a sense, this express, two things are really happening. The state updates, initialization of x, and the restoration of x happens between the execution of the before C and after C. So that's how we capture this in this continuation semantics. So what's going to happen after C is expressed in this the change in the continuation. Okay, so that's in the top continuation semantics. And here's the third part. So how to handle fail in continuation semantics. So especially in the presence of new variable declaration. So how to handle this? And then you might think that, okay, the handling failure is not very difficult. What fail is supposed to do, fail is supposed to ignore the rest of the computation and just run so it just ignores the rest of the computation. So the continuation semantics of fail, you might say it takes kappa and stays sigma, and then you just return the sigma. So I say I abort sigma. So this is possible candidate. But this candidate turns out to be wrong. Okay, it has a problem. So especially with respect to the new variable declaration. So what the problem is? So the problem is like this. So if you declare a new variable, say, and then if you just fail, kappa and sigma. So we are expecting the output is going to be the same as, this is an expected output. So, and that's because we hope all the things that we do the local variable, even in the presence of this failure, get restored properly back to the, get all be undone properly, and then the value of the global variables get restored. And in actual computations, in actual computer, that's actually what happens. That's because in an actual computer, the memory, all the local variables are allocated in a computer so-called stack. So if you have a global variable x here, then local variable is stored in something called the stack. And when we do fail, which is very much like an exceptions. So if you have an uncut exception, then all these stack will disappear. Okay, all these things will be popped, and then the value of the global variable will returns to the user. Okay, so that's what happens. And then another things that we want to ensure in the semantics of this language is that this one should have the same meaning as new var y1 in fail. It's because we hope and we want the name of local variable shouldn't really matter. Okay, so that's what we are expecting. But it turns out if you just take the definition above, that's not the case. That's because although I'm not going to do the calculation, if when you do the fail, then this fail, completely ignores what's surrounding, and then it just stops with the current state. So if you take this definition, what's happened is that, so if you take this approach, what happened is that the one above will give the value which is I abort, where sigma has the value, where variable x will have a value 1, and the below will have an I abort, where y will have a value 1. So they are not the same. So name of the local variable start to matter. So what should we do? So that's the problem. It's more like problem. And one solution of this problem is to have two continuations. As parameters to the semantics. So if you now think about this abort, there is actually some work needs to be done after this fail. There are some work that needs to be done. What's that work? The work is to restore the value of the global variable. Okay. So in a sense, we need to have a record, the idea of this solution is to record two kind of summaries, two kind of information about what should be done in the rest of the computation. One is the usual description about what needs to be done by the rest of the computation. The second is what kind of the restoration of the global variable values should be done after this computation. So we pass two continuation. One is about the rest of the computation. The second is about restoration of global variables. Okay, so that's what how to solve this problem. And actually, this type of idea appears quite a bit, and sometimes it's called double-barreled continuation passing style semantics. And so here's this new semantics of the command continuations. Let's call it 2. It takes command, and then it takes two continuations. Okay. one is sigma omega. And then second, this is the second continuation. And you take the current states and returns the final outcome. This is the usual continuation. And this is a continuation for fail. So another way to think about this second continuation is that's a continuation that knows how to restore the value of global variable. Sigma is the input state. And then omega is the final answer. Okay, so that's the setting. And then this semantics is defined this way. So it takes two continuation. One is for, I write it as a T and kappa F. And then it takes input state sigma, and then it writes something. And it's defined in a syntax directed way. For skip, most of the case, it's like the one before, original continuation semantics, where we only use a kappa T. Okay? So essentially the repetition of the semantics of what we have done before, except that we are using kappa T. So here's an example template about how they actually look like. So kappa T, and then we just pass sigma. And the semantics is defined this way. So we have assignment case, same. Kappa F, sigma. It's also run kappa T, where the sigma is updated to have updated by this assignment. And then sequential composition and others are very, very similar. F. So actually, I mean, this for sequential, I mean, maybe I put it as an exercise. Let's see, two continuations, kappa T, sigma. And so what I want you to do is I want you to fill in the rest. So what's in the semantics for C1, C2. I will write the semantics of fail for fail, because that's the whole point of having this kappa F and sigma. We are not invoking kappa T, instead we are invoking kappa F with the current state sigma. So this is the important part. I mean, kappa F is only used by fail. And nearly all the rest looks the same. Except some, I'm gonna skip, what is it? I mean, input and output, because they follow the similar pattern. But one major difference is the new bar has to be changed, okay? This one needs to be changed. That's because the new bar is the one that should introduce how to restore the value of the global variable. So this kappa F has to be updated as well as kappa T. Okay. So here's an exercise for the remaining 3 minutes. Fill in the, for if then else case, while case, and then this new bar case and sequential composition case. Okay, so let me tell you how to solve this. For sequential composition, we are only updating the true part, okay? Because, I mean, for variables that needs to be restored, they are statically scoped. So for C1 and C2, we're gonna use the same restoration mechanism of the global variable. So here we have, we run C1 under this continuation second. Then we only update the first continuation part, and then that updated continuation is by C2. And then the restoration part remains the same. And for if then else, it's exactly the same as before. Just use red. So if Boolean is true, so then we on C1 the continuation semantics with both continuation unaltered on the sigma, otherwise we run the fourth branch. Okay, and then for this new bar is actually the most important part. We run the body C, but both continuation is changed. So the continuation for the true branch, continuation for the normal terminal executions that incorporates the restoration mechanism of the global variable. So this prime variable x has a value something like this. And then for the failure continuation, do the same thing. So what this means is that this new bar is the only guy that's gonna touch this KF part. And that's what we expect because KF only record how should we restore the value of the global variable. And then the starting state is changed. So the sigma has, it's not working. So sigma has the variable x has a value at initialization. Okay. So that's what C2 do. And for the while loop, so we can use the fixed point over this space and run it sigma. And then the fixed point, definition of fixed point exactly the same as before. So f take kappa prime, and then also sigma prime. If loop condition is true, and we run the body of the loop under this continuation to semantics, and then we provide the failed continuation fixed is same as the input one, it's not changed, but then the normal case continuation is replaced by kappa prime, and that's exactly what we did before. Otherwise, we normally terminate, so we call this continuation that's given as an input, and with the state sigma prime. So that's how we define, and that's the semantics of this while loop. So I think I have about 1 minute. So what I want you to think about, although I'm not going to solve this, is actually first try to do the same thing that I did before. So here are some more open-ended exercise. So, and then first state, the relationship, formal. between the C. This is second continuation semantics in the presence of new variable declaration and fail, and just usual semantics. This is a bit different from the one that you studied before, but it's a bit similar. But you need to be a bit more creative to solve this exercise. And second exercise is, now once you state the formal relationship, show sorry. The relationship hold for a language without loop. So that's a second exercise I want you to try. And then finally, if you solve both of them, maybe think about how to include the loop. So I think the best, really really appreciating the role of continuation, its power, is really play with it for a while. And then one way to play with the continuation is to solve a few exercises in the setting, or if for continuations in programming languages, actually write programs that uses continuation. Okay, so that's it for today. And as I announced in the beginning of this course, there will be no midterm exam. And I hope all of you do very well in the midterm exam, and then see you all in not next week, but 1 week later. Okay, so that's it.